Welcome everybody. No? Welcome everybody. Welcome for this presentation about C++, metaprogramming and obfuscation. My name is Sébastien Drivet. I'm cyberfeminist activist. Professionally, I'm specialized in reverse engineering. I'm doing also some pen tests, especially on mobile devices, iOS and Android. I'm doing also some forensic, and I'm C++, C, C#, Objective-C developer. Since beginning of this month, I'm working for a company called SCRT in Switzerland, near Lausanne. And SCRT is the organizer of Insomniac in Geneva. So why I'm talking about obfuscation? What is the problem? I was supposed to make a demonstration, but you notice that I had some problems with my laptop. So I record a video. Sorry for that. This is IDA. IDA is perhaps the best decompiler and disassembler. And I open in IDA an iOS application. It's an agent for a mobile management system, a well-known mobile device management system. And mobile device management systems are there to enforce company policies. And in this case, it makes jailbreak detection, and it enforces the integrity of the device. And I will show you how to find the code responsible for this detection. So I will start the video. So this is IDA. And I will search for a string. The string I will look for is Cydia. Cydia is a well-known, I will just stop the video here. Cydia is a well-known, it's the equivalent of the Apple App Store for the jailbreak market. And the idea is to, instead of decompiling and try to understand the whole agent, the whole application, I will just try to find where this string is used. So I find the string, and I will look for cross-references, so code which is using this string. So now I have another string, an Objective-C string, and I find very quickly the code responsible to detect if the device is jailbroken or not. I can even use a decompiler, and I will not get Objective-C code, but something which is close to C code. And you see a list of strings, and a little bit later, you see a file exists at pass. So this application is just looking for a list, hard-coded list of files, and if one of the files exists, it will suppose that the device is jailbroken. It's very easy to patch this function to always return false, and then you can reassign the binary, reinstall on your device, and you have a device which is jailbroken and which seems to be compliant for the MDM. And this is exactly the situation I wanted to avoid. It's too easy to find this kind of code, and I wanted to make something. And one solution is obfuscation. Sorry. So what is obfuscation? If you take a software, an application, for example, in this case, application will be called Katy Perry, and you have an obfuscator O, which is like a mathematical function, and you apply this obfuscator to Katy Perry, and you get another Katy Perry. It's still Katy Perry. It's really Katy Perry. It has almost the same semantics, almost the same side effects. Perhaps it's a little bit slower or things like that. And it's obfuscated. In a more formal way, obfuscation is a deliberate act of creating source code or machine code difficult for a human to understand, and it implies that it's not difficult for a machine to understand and to execute. There are different classes of obfuscator. You can transform the source code and you can transform the binary code. It corresponds more or less to the different phases of a compiler between the front end and the back end. And inside the first class, source code transformation, you can manually make the obfuscation, but it's difficult to manage. After, it's difficult to debug the application. You can use a preprocessor. You automate for example, for strings literals to obfuscate or encrypt string literals, you can try to make a list, and your preprocessor will replace each string by another one, etc. But it's not very easy to manage, and it's very difficult for the developer to debug. And you have also abstract syntax tree obfuscators. When you compile, it depends on the language, but normally when you compile source code, it generates an intermediate representation of the source code, which is independent of the platform. And you can obfuscate code at this level. And for some languages, you have more phases, more possibilities. And C++ is a case. You have C++ template instantiation, and I will use that for obfuscation. Before going into an implementation, I will explain a little bit what is C++ templates. If I take an example of a stack of objects, I want to develop a class, some code to represent such a stack of objects. You have two methods, push, to push an object on the top of the stack, and you have pop to remove the object on the top of the stack. So if I try to make a class representing a stack of anything, I'm declaring my class with struct. It's almost the equivalent of class. And I have two methods, push and pop, and you need to pass as a parameter the object, and I want to make only one implementation, so I have to accept anything, so I put a void pointer. A void pointer is a pointer to anything. And to use my stack, it's simple. For example, I instantiate a class called singer, and I put this in a variable called Britney Spears. I can push Britney Spears on the stack, and later in my code, I can retrieve this object. I can call a method of singer, a singer sing, and it's working because in this case, the singer is Britney Spears. If I take another example, this time I instantiate an apple, and I put my apple on the stack, on the same stack. It's possible because I'm accepting anything. And later in my code, I pop the objects, and I put this in a variable called Justin, and it's a singer, and I can call sing on my object because a singer is able to sing, but it will not work, it will crash, or it will behave very strangely because in this case I have an apple, I don't have a singer. This is exactly why C++ templates have been designed. It's to avoid this kind of situation. The goal is to have only one implementation which you can apply to any object, but with type safety. So instead of declaring a void pointer as a parameter, you declare a template for a type name called T. You can put any name. The convention is to put only one letter and in uppercase. And you replace your void by T, and this time, if I try to push an apple on the stack of Singer, I will have a compilation error, not a runtime error, not a crash. I have a compilation error. There are different kinds of templates. In this presentation, I will focus on class templates. And you see that you declare a template with this syntax. You type template and angle brackets. And you have a list of parameters. You can put types with the prefix type name or class. It's exactly the same. Or you can have integral types like integers, shorts, long, enumerations, etc. It's not working with double and float because they are not integral data, integral types. You can also put pointers and references, and you can also pass as a parameter another template. You have a template of a template. It's sometimes used, but it's not very often. I will give an example of a class with an integral parameter. For example, I'm trying to represent the Fibonacci sequence at compile time, not at runtime, at compile time. The Fibonacci sequence is related to the gold number and things like that. It's simply the sum of the previous two items in the sequence. And if I try to represent this with C++ templates, I'm declaring a struct, a class called Fibonacci. And I have an integer, which is called value in this case, and value is simply the sum of the previous two items in the sequence. And to reference, to compute these items, I'm referencing to the same template. So it's a recursive template. And the recursion has to stop somewhere. So I'm declaring after two special values for 1 and 0, with the value 1 and 0. And this way, when I instantiate, for example, Fibonacci for 20, it will iterate. It's not an iteration, but it's a recursion. It will recurse and instantiate templates for the different values, and it will stop with value 1 and 0. And if I look at what I have in the binary, I will only have the result. Everything is made at compile time. It's very different from this declaration, which is a normal function. It's more simple, but it's a normal function. And this function is evaluated at runtime. So the compiler will generate code for that. And what is in orange is evaluated at compile time. No CPU, nothing. Everything is at compile time. So this is what is called metaprogramming. You are able to manipulate the compiler, the C++ compiler, to manipulate types, to generate programs. It's written with a subset of C++. It's completely part of the standard. It was proven to be Turing compatible, and it's very close to functional programming. For example, you don't have loops. You see in the previous example, you have to use recursion to emulate loops. And I will now show you first implementation. In the small video I show you at the beginning, you see that it's very easy to find some code with strings. You just follow who is using a given string, and you find interesting code. And like I said, it's what I want to avoid. And this is some how to say that? This is my goal. With my implementation, I wanted to have the string, the original string, in the source code. Otherwise, it's too difficult to manage and to debug. The original string has to be in the debug builds, but has to disappear completely from release builds. And I will show you how to implement this with metaprogramming. So this is a first implementation. I will describe each line. So I'm declaring a class. It's called struct, but it's like a class. The difference is that everything is public. And it's called metastring, one because it's the first version, and metastring, it's just to store my obfuscated string. And the second line is a constructor, and with a parameter, which is my original string. I need to store the obfuscated string somewhere, so I declare a buffer characters. We will see the length after. And in my constructor, I have to fill this buffer. So I'm declaring that the buffer will be filled with the values which are after the braces. And what I want is to encrypt each character. So I'm taking my string, original string, which is str, and I have to take each character. If I If I take an example, if I have 3 characters, what I need is to extract the character at position 0, then at position 1, and for each case, I have to call encrypt. And I don't know in advance the length of my string. It has to work with any string, any length. So I will use what is called a variadic template. I just put 3 dots after the int in the template, and then I'm using the 3 dots in the constructor, and the compiler will just replace these 3 dots with each index I have in my templates. So I will call my templates with a list of index 0, 1, 2, 3, etc. And the compiler will just iterate this list of index and will replace the 3 dots by this code. I have also another operator which is a size of with 3 dots, and it will give me the length, the size of my list of indexes, and I put +1 because I want to put a null byte at the end. I have an encrypt function, an encrypt function member. In this case, it's just an example. I'm doing a XOR with a hard-coded value. And since it is a XOR, the decryption is exactly the same. And everything in blue is evaluated at compile time. So the compiler will take my string, will extract at compile time each character, will encrypt each character, and will store the result. And I need to decrypt this at runtime, so I'm just declaring decrypt. The implementation of decrypt is trivial. It's just a loop, and I just have to call decrypt for each character. And to use this string, I'm declaring a macro, and you see a list of index, and so it will create an instance of this class with original string, and then I call decrypt. So everything will be evaluated at compile time except decryption. And to use my string, I just put this kind of prefix, obfuscated one, and my original string. However, I have a small problem with this implementation. Like you see, the list of indexes is hard-coded. And if I have a string which is longer, it will be truncated. And if the string is shorter, depending on the compiler, it could produce very strange things. So I have to enhance my implementation. What I need is to be able to generate at compile time a list of indexes. With a future version of C++, it will be possible. It will be part of the standard. It's called index sequence, but unfortunately, it's a future version of C++, and I need to use compiler of today. So I have implemented myself a very simplified version of this template. I will not explain how it works because it's a little bit complicated. But what is important is the result. If I call makeIndex with a parameter n, so any integer, and I retrieve the type of that, I get a template called indexes, and the parameter of indexes are my sequence of number. So in my first implementation, I can replace the list, the hard-coded list of integers by this makeIndex, and it works. But I still have some limitation in my implementation, because as you see, the key is hard-coded. What I want is to be able to generate a different key for each string and, if possible, also for each compilation. And to be able to do that, I'm just adding a new parameter to my template called k. And I have a metastring 3. And I need to generate at compile time pseudo-random numbers, or random numbers, to simplify. So I've created another template, which is called meta-random. I will not go into the details of that. It's not very complicated to implement. In this case, it's implementing a linear congruential engine. It's not a uniform distribution because it's not so easy at compile time to make a uniform distribution, and it's not very important in this case, I think it's not very important. So the bias is very small in this case. And it's a recursive template. So to use meta-random, you put, you have a maximum. For example, you want to generate a number between 0 and 5. You will put 6 for m, because you generate a random number in a set of 6 possibility. And to get the first random number, you just call the template with n equals 0, etc. And in the case of when the n is 0, I need a seed. It's not a true random number generator. It's a pseudo-random number generator, so I need a seed. And the seed has to be different for each compilation. And you have only a few possibilities in C++. At least I find these possibilities. It's to use two macros, two predefined macros. One which is standard, it's the time, the compilation time. And the second one, which is called cantor, it's not standard, but it's implemented by the majority of compilers. It was first introduced by Microsoft, if I remember well. Counter, you have, when you instantiate or when you reference first time counter, you have 0, and when you reference a second time, you have 1, etc. It's a counter. So thanks to time, I can generate different keys for each compilation, and thanks to counter, I can generate different keys for each string literal. So I have almost a perfect solution, but why not go further? In what you see in this example, my algorithm to encrypt is always the same. It's just XOR. But why not using a different algorithm for each string and for each compilation? And it's possible with exactly the same principle. So I'm introducing another parameter called A, and I will use what is called template partial specialization. I will make an implementation for a special value of A. So my first implementation is with when A is equal to 0, and the second one when it is equal to 1, etc. In the example, I have only 3 implementations, but you can imagine a lot of different implementations. And to choose a random algorithm, just using again meta-random. In this case, I have only two possibilities, two algorithms. So I have the value 2, but you can implement the number you want. And this is my code without obfuscation and my code with obfuscation. So the syntax is not so nice, but it's not too ugly. And I will show you the result. Again, I was supposed to do that in live with IDA, but unfortunately, I was not able to use my laptop. So I will just show you some screenshots. So this is the original implementation. And you see the original string, Britney Spears. And this is the equivalent after my encryption. Perhaps it's not very obvious to see, but I have a mix of instructions, move, and obfuscated values, because it's generated directly by the compiler. In my implementation, I have an array of characters, but it's optimized by the compiler, and as a result, you have a mix. So in my binary, I don't have the original string, but I don't have also the obfuscated string. It's mixed with instructions. And then I have a third block, and this is a decryption. So it's very small because my implementation is very simple. In production code, it's not bad to have something which is simple because you are introducing some computation which are not part of the original program. So you have to find a good balance between complexity and speed. I will then show you quickly a second application of this principle. My goal in this case is to obfuscate calls. I have a function, and in this function I want to call another one, which is called in this case function to protect. And I want to protect this against static analysis and even dynamical analysis. Of course, it's not perfect. What I want is to slow down reverse engineering. For that, I will use a finite state machine. The principle is to generate a lot of code, complicated code, difficult to follow. I have a very simple finite state machine in this case. In production, it will be more complex. And my entry point represents the call at the source. And in my example, the final state represents the call in the target. And in the middle, I'm generating, the compiler will generate a lot of code. To do that, I'm using library from Boost. Boost is a collection of C++ libraries. And they have a library which is called metastate machine. And I'm declaring simply a transition table. It's still C++, and it's completely evaluated at compile time. So the compiler will use this state, this transition table, and with that, it will generate code to implement a finite state machine. Things like state or events are classes. They are not values. They have no meaning at runtime. They have meaning only at compile time. And to use my obfuscated call, again, I have introduced a macro. And normally, you call the function, you type the name of the function, you put a parenthesis, and you have the parameters. With my obfuscated call, you have to put this prefix obfuscated call, and the name of the function is the first parameter of what is look like a function. So the syntax is not so nice, but in my point of view, it's not too ugly. And if you want to combine the obfuscation of the call and the obfuscation of the parameters, you have the last line. So this is the code without obfuscation. You simply, you don't, in this case, you don't have an actual call, it's a jump because it was optimized by the compiler, but it's equivalent. And if I take the example of my obfuscated call, it's only a small subset of the code generated by the compiler. In my implementation, I have even obfuscated the address of the target, because in IDA you see that it's very easy. IDA is able to compute cross-references. So if I have the address somewhere, it will find it, and I will be able to make static analysis and to know who is actually calling this function. So I obfuscate, it's simply a shift of the value. And using the same principles, it's possible to go even further. Like I said, I have obfuscated the address of the target. It's possible also to use several different finite state machines. It's exactly the same thing like for the metastring, for the string obfuscation. I can define a set of finite state machine, and at compile time, the compiler will choose one randomly. And you can imagine that it becomes more complex for a reverser to be able to reverse. It's still possible, but it's far more complex. And something which is interesting with finite state machines is that you can combine transitions with values like debugger detection or virtual machine detection. So in a transition, when you execute the finite state machine, if it detects that debugger, for example, is running, it will follow a different path in the finite state machine, and you can enter a loop, infinite loop, for example, or something like that. Some words about compilers support. What I've implemented is well supported by Apple LLVM, like C-Link. Even the latest version, it's well supported by the normal LLVM. It's also supported with GCC and the Intel C++ compiler. For Intel, I think that you have to use the latest version. Unfortunately, it's not supported with Visual Studio because the Visual Studio is not supporting well C++11. They have a lot of difficulties to implement constant expression which are evaluated at compile time only. It's an old compiler, and apparently they have some difficulties. Even in the latest version, the technical preview one, it's still not working. I think it's possible to change my code and to port this to Visual Studio, but it will become very ugly. It will no more C++11, and I didn't have the time, and in my case, I was using Apple LLVM, so Visual Studio is not so important for me in this case. You have to be careful with your compiler options, because if you are not paying attention, the compiler may generate some debug code, and in the debug code you will have the original string, for example. So it's important to use in release the right options. With the GCC, it's not C++11 by default. You have to specify this on the command line, and you have to use optimization function. I think that I have a mistake. It's not S, it's -S. For Xcode, you just have to check the deployment preprocessing. Otherwise, a lot of optimization are not applied to the binary code. In some cases, it's better to disable RTTI. In C++, you are able to, at runtime, sorry, you are able to know the exact type you have. You are able to interrogate your own type system, and it will generate a lot of information for attackers. Unfortunately, my finite state machine implementation is using RTTI, so it's possible to remove them for obfuscated string, but not to obfuscate calls. Of course, there are some drawbacks of my implementation. You have to use a C++ compiler and a C++11 compliant compiler. Some parts of your application has to be in C, C++, or Objective-C. It's working very well with Objective-C because, at least if you are using Apple Xcode, they support natively what is called Objective-C++. If you take a normal Objective-C file, which is with a .m extension, you just rename to .mm, and you have an Objective-C++ file, a mix of C, Objective-C, and C++. The obfuscation will increase the executable size. You see an example before and after obfuscation. So it's not a good idea to try to obfuscate absolutely everything. It's better to focus, make it again. It's better to determine what is really important in your code. It will increase compilation time. For the obfuscation of string, it's not so much. For the finite state machine, if you have a big finite state machine, it could be a problem, especially with the Intel compiler. The Intel compiler is a little bit slow. One major drawback is that obfuscator, this kind of code, is complex to write and complex to debug. You are not debugging with a normal debugger because debuggers are running. It's at runtime. Instead, you have a list of strange error messages, and it's not always obvious to understand really what is wrong. It's better with the latest compilers. Error messages are better with templates. However, it's not so simple. And I didn't find a way to apply some obfuscation techniques with metaprogramming, especially control flow graph flattening. It's better to do that at another level, at the level of the intermediate representation of compiled code. And there are some benefits. You don't have to use any external tool. You don't have to use modified compiler. There is a project which is called LLVM Obfuscator, which relies on a modified compiler. It's developed in Switzerland, in Yverdon. But each time Apple is releasing, Apple or anybody is releasing a new version of the compiler, you have to reapply, to retest, etc. The advantage of my approach is that it's completely standard, so you don't have this kind of problem. It's independent of the target platform, but this is from the compiler. And this obfuscation is at the source code level. It's a high level. So it's possible to make some very complex obfuscation. For example, an idea is to split a finite state machine into different pieces to execute this at different time, even in different threads. And it's not completely hidden to the user of the library, but almost. So you can have things which are very complex and code which remains manageable. It's also possible to use this kind of techniques with iOS and Apple App Store. There are some other obfuscation techniques like virtual machines or the decryption at runtime of portion of code. But these kind of things are not possible if you want to publish on Apple App Store. It's forbidden by Apple. And using my techniques, it's possible to make obfuscation despite of these limitations. I'm continuing my researches. I try to apply, I just give 2 examples, and I try to apply more obfuscation techniques. I try to find a solution to apply this to Objective-C. Objective-C is a dynamic language. When you call a method, in fact, you are sending a message, and this message, the name of the method, is in the binary, and it gives a lot of information for an attacker. And I try to find a way to be able to encrypt this method name. And I'm also working for a solution for Android. Of course, Android is written in Java, but it's possible to call some C or C++ code, and I'm working on a solution for this platform. All the code presented here are available on GitHub, and the code contains obfuscator and some examples. It's released under the BSD license, so could be used in almost any project. I have also a white paper, which is also available on GitHub, which describes in more details the obfuscator. And this is my contact, my email address and my Twitter account. And this is the end of my talk. Any question? No? Okay, thank you. No? Ah, okay.
What's the impact on compile time?
Sorry, can you repeat?
What's the impact on compile time?
It's very dependent of the compiler. Frankly, I don't have any clear numbers because it depends. If you are applying these techniques to the code everywhere, of course you have some impact. What I see is that with Apple LLVM, it's not noticeable, but for Intel compiler, it will increase, it will double the compile time with a finished state machine. Another question? No? Okay. Thank you.